you who missed the concept, we will solve many problems to emphasize the importance of Laplace transform. So now today we will use Laplace transform in solving differential equation. And basically, this is our purpose. Why we give you Laplace transform? This was the purpose, or to solve differential equation, or to solve mechanical system or electrical system or anyone. So just an example, solve the initial value problem. When you see this one, initial value problem, IVP, this one stands for initial value problem, which means the initial values are given. Given a differential equation of this type, y double dash plus 6 dy over dt plus 8y is equal to 2. And we have the initial conditions, y0 is equal, y dot 0 is equal to 0. So the initial conditions are 0. If we take Laplace transform of the second derivative, you remember, Laplace transform of the second derivative, when we differentiate Laplace transform of the second derivative, we said Laplace transform of the second derivative is simply s squared y of s minus s y of 0 minus y dot of 0. Now, if the initial conditions are 0, y0 is equal to y dot 0, this term disappear, it will be 0, and this term disappear, it will be 0. So Laplace transform of the second derivative will be s squared y of s. That's why we are taking here s squared multiplied by y of s plus 6 is here, dy over dt. Laplace transform of the first derivative, Laplace transform of the first derivative is simply s y of s minus y of 0. Y of 0 is 0. So since the y of 0 is 0, we will end up by having just s y of s. That's why we have 6 s y of s. Laplace transform of 8 is simply 8 times y of s. So we have one equation now that's turned to be algebraic equation. This algebraic equation, s squared y of s plus 6y of s plus 8y of s is equal to, this is 2, it's a constant. Laplace transform for it is simply y of s will be simply 2 over s. 2 over s is Laplace transform of 2. So now if we just take the algebraic equation, it turns to be s squared plus 6s plus 8 is equal to 2 over s. Now, if we solve for y of s alone, we will find it like this. 2 over s times s plus 2 times s plus 4, where s squared, if you remember, we wrote this one, s squared plus 6s plus 8, we wrote it as is equal to s plus 2 times s plus 4. We wrote it in this form. So this s squared plus 6s plus 8 can be written as s plus 2 times s plus 4. So we have, as you can see here, we have 3 poles. S is equal to 0, s is equal to minus 2, and s is equal to minus 4. These poles are real and distinct. So we can use the partial fraction alpha over s for this pole, beta over s plus 2 for this pole, and gamma over s plus 4 for this pole. Now, need to find what is alpha, what is beta, and what is gamma. I left alpha, beta, and gamma as an exercise for you. You will find them. So at the end of the day, we found alpha is equal to 1 over 4, beta is equal minus half, and gamma is equal to 1 over 4. So y of s is written like this: 1 over 4 over s minus 1 over 2 over s plus 2 plus 1 over 4 s plus 4. Now the inverse Laplace transform, which is y of t. So now we will be moving from s domain to time domain here. through the inverse Laplace transform, when we take the inverse Laplace transform, this will give me 1/4 constant, and then minus half e to the minus 2t, and then plus 1/4 e to the minus 4t. And this is your solution y of t in time domain. So you solve now the differential equation in time domain just by using Laplace transform. Any question? Any questions? So we move to the second problem. No questions, so let me move to the second problem. We have another problem here. Solve the initial value problem. Initial value problem, y double dash, second derivative of y with respect to time, plus y, so y double dash plus y is equal to t. And these are the initial conditions. y0 is equal to 1, and y dot 0 is equal to 1. So now if we take Laplace transform of both sides of this equation, both sides, Laplace transform of the second derivative of y will be s squared y of s minus s y0 minus y dot of 0 plus y over s is equal to 1 over s squared. Here, the t, because we have t, Laplace transform of this is, the t is simply the ramp. Laplace transform of t is equal to 1 over s squared. That's why we have the 1 over s, it's from here. It's coming from here. 1 over s squared, it's coming from here. Laplace transform of t. So this is the Laplace transform of the second derivative, s squared y of s minus s y0 minus y prime of 0 plus y of s is equal to 1 over s squared. Now we substitute the initial conditions. What is y0? y0 is given to be 1. What is y dot 0? Y dot 0 is equal to be 1. We substitute this and we take s common. If we take s common from here, s squared y of s, and we have y of s here, so it turns out to be s squared plus 1 y s. The right hand side we have 1 over s squared here, and we have s times y0, s times y0 will be s, and we have y0 will be 1. So this is the right hand side and this is the left hand side, and this is your algebraic equation. We wrote it now in algebraic equation. In algebraic equation, just solve it for s. When we solve for s, we got this equation. We got this equation. Y of s will be simply, y of s here will be 1 over s squared times s squared plus 1, and this term will come here. And then here we divide by s squared plus 1. And then we divide by s squared plus 1 also here. So at the end of the day, we get this equation when we solve by s squared plus 1. So here, now I just give you some explanation aside. This one, it will be aside before we move. So if we take just this polynomial, which is the red one here, if we take it, and we write it in partial fraction, this polynomial 1 over s squared plus 1 can be written in this form. 1 over s squared minus 1 over s squared plus 1. So instead of this one, the red one, I will write it by its equivalent, 1 over s squared minus 1 over s squared plus 1, which is this one, the red one. The green one will stay as it is, green, and the blue one will stay as it is, green. علي البشر تفضل.
دكتور ما فهمت كيف تحولت الى الشكل الثاني 1 over s square minus 1 over s square plus 1.
Just write it. This is an exercise for you. Just write it like this: a over s squared. You have two poles in there. You have one pole. You have b over s, and then plus c over s squared plus 1. Write it this form, and you will get it. We cannot go into the details because this one from last lecture, we cannot go through all the details. We will go just to what we are concentrating on. This is an exercise for you. You can work on it and find it. واضح? Or you can if you multiply this together, if you multiply these two together, you will find this one the other way around. You can do it as an exercise for you. So the red one will be written like this. The green one is here, and the blue one is here. Now we have 1 over s squared plus 1, and you have minus 1 over s squared plus 1. This turns out to be 1 over s squared plus s over s squared plus 1. You know, this one will be simply, we need to look what is the inverse Laplace transform of this, and what is the inverse Laplace transform of this one. The inverse Laplace transform of 1 over s squared is simply t. The inverse Laplace transform of s over s squared plus 1 will be cosine t. So this one will be cosine t, and this one will be t. As I mentioned, this one, Shabab, you can do it by the partial fraction. If you remember, we have done last time partial fraction. I cannot give you all the details for each exercise. Otherwise, we will be wasting our time for things that I have already gave you. So I assume now you know how to do this. I assume you know how to get the partial fraction. واضح شباب? Now, if you look to the previous problem that we just solved now, they were asking us in time domain, the differential equation was given in time domain like this. Y squared plus y double dot plus y is equal to t. These are the initial conditions. From time domain, we went to the S domain through Laplace transform. We took Laplace transform of both sides. We found this, and then we solved for y of s, and y of s, we found it like this at the end. And then back to the inverse Laplace transform, we found the solution t plus cosine t. And this is how the Laplace transform works. This is, if you remember, was one of the first slide I gave you when we started Laplace transform. So this is the method how we can solve Laplace transform. When we are dealing out in system dynamics and control, we will do the modeling. The modeling, we will find a differential equation in time domain, like this, something like this, and then we transform it to S domain, and then we solve for the S domain equation, and then we take the behavior or the time domain solution. After that, if we see that this time domain is not behaving well, or it's not what we want, we will try to control it, to impose the control on it. So we will see in the control part how we can control this response. Is this clear, Shabab? Any question before we move to something else? Any question? Any question? So another differential equation or another system to be solved, x double dash. You will have your quiz on Tuesday, inshallah. We will be asking you to solve something like this. So I want you to concentrate on this one. Here we have x double dash, the second derivative of x, plus 4x dash plus 3x is equal to exponential minus t. And we have the initial conditions, x0 is equal to x dot 0 is equal to 1. Yani both x0 is equal to 1, x of 0 equal 1, and x dot 0 is also equal 1. So we substitute, this is this expression is Laplace transform of the second derivative, Laplace transform of x double dash is this one, s squared x of s minus sx0 minus x dot of 0 plus 4 here, the 4 is here. And then we have Laplace transform of the first derivative. This is Laplace transform of x dot. And then plus 3 is here. 3 is simply x of s. And you know Laplace transform of x minus t. Laplace transform of x minus t is simply 1 over s plus 1. So if we take Laplace transform of both sides, we end up by this equation here. Now, if we solve for x of s, here now we have x of s, here we have x of s, and here we have x of s. If we solve for x of s, we will find the following. We will find s squared plus 6s plus 6 over S plus 1, S plus 4, S plus 3. Here now we can see the denominator, this denominator. If we solve for this denominator here, we will see that our equations, we will see that we can solve for the poles. The poles here now we have S is equal to -1. And if you split this one, you will find it that this one is simply S plus 1 times S plus 3. So I can erase the board now. I'll just write here S squared, this term S squared plus 4S plus 3 can be written as S plus 1 times S plus 3. So I will write it here for those people who S squared plus 4S plus 3. It can be written like this, S plus 1 times S plus 3. So the denominator كله, this denominator, all the denominator will become S plus 1 times S plus 1 times S plus 3. So we'll have 3 poles basically. This is one pole, S is equal to -3, and this is S plus 1, and S plus 1 is a double pole, the double pole like this one. So it's so S12 is -1, a repeated pole of order -2 or of order 2, and this one is a pole for order 1. So we can write our equation in this form: A over S plus 1 plus B over S plus 1 squared plus B over C plus 3. Because this one, because we have a double pole here, because of this double pole, we can write this one. This is because of the double pole, S is equal to -1. So A over S plus 1, B over S plus 1 squared. And this is for the pole that is equal to S is equal to -3. When we did the partial fraction, these are left as an exercise for you. When we did the partial fraction, we found A is equal to 7 over 4, B is equal to half, and C is equal to -3 over 4. So now we can write our partial fraction: 7/4 over S plus 1, 1 over 2 over S plus 1, 2 squared, and then -3 over 4 over S plus 3. The inverse Laplace transform of this one simply turns out to be 7 over 4 exponential minus t, because this one S plus 1. And then since this is S plus 1 squared, so 1 over S squared is t. 1 over S squared is t. But 1 over S plus 1 squared is t exponential minus t, because this is shifted by 1 here. So half t exponential minus t minus 3 over 4 S plus 3, yani it will be -3 over 4 exponential minus 3t. And this is the solution of your initial value problem. Any question, Shabab? Here we have another system, another problem that is mass spring damper system. And then we have the input to the system, or the forcing term, the right-hand side here. The right-hand side is given by this function here, shown here. And this equation of motion is for the system shown here. Mass times a damper plus the spring. We will see, inshallah, when we study the chapter 3, we will see how we will derive this equation, how to find it, using either Newton's second law or using the energy equation. Energy equation cannot be applied here because we have a damping, or we can see Lagrange equation. Now, what is important for us is to solve this one, not the derivation, but the solution for this equation. The solution for this equation, just assume we have the initial condition, 0 initial conditions. They are given to us to be 0. So x0 will be equal to 0, will be equal to x dot 0. So, and Laplace transform of t, f of t now, f of t is given by this. This one, if you remember, it's the pulse. The pulse, we found the Laplace transform for it to be f naught. This is the amplitude, times 1 minus e to the minus t0s over s. So, or you can look at it as it is f naught, magnitude f naught. It is a step function that starts at 0, minus another step function that starts at t is equal to 0 late. So either this or this, we can find the Laplace transform for it, which is given by this equation. Now, if we take Laplace transform of both equations, we will get ms squared plus cs plus k times x of s is equal to f0, 1 minus exponential minus t0 s over s, which is the right-hand side here. Here, the differential equation, Shabab, was like this: x double dash plus cx dash plus kx is equal to f of t. Because the initial conditions are 0, when you differentiate the second derivative, so if you differentiate Laplace transform of mx double dash for 0 initial conditions, you will get this one. For 0 initial conditions, Laplace transform of x double dash will be simply s squared x of s minus s x 0 minus x dot of 0. And this one will be simply, since this is 0 and this is 0, this turns out to be m simply s squared x of s. That's why we are multiplying. And m s squared, it will be m times s squared. Similarly for the first derivative. So if we solve for x of s now, we will find the following. If we solve for x of s, the equations turns out to be this one. X of s will be 1 minus exponential minus t0s times f0 over s ms squared plus cs plus k. We can look at it as this one can be written in this form. It can be written as this term, f0 divided by this. This is, we are calling it x1 here, x1. Multiply by this, which is x2. Yani this one will be minus f naught t0s minus f naught t0s over s times s squared plus. We are calling it x2. This is x2, which is minus x1 times exponential minus t0s. So now if we assume we give values, numerical value to m, c, and k, we can write the equation like this: ms squared plus cs plus k turns out to be s squared plus 2s plus 5. And the poles here, or the roots, turns out to be complex conjugate. Then you can write s squared plus 2s plus, you can write it like this, plus 4 plus 1. This one, you can write it like this: s plus 2 the whole square, and then plus 1 is equal to 0. If you solve this equation, you will find these this is the solution. It is complex conjugate. So these are complex conjugate poles. And now all we need to know is to find what is x1 and what is x2. Once we find x1, once we find x2, we add them together, we will get the solution x of s. So this is what we got at the end of the day with the equation. X of 1 is f0 divided by s ms squared plus 1. S squared ms squared plus cs plus 1, we wrote it in a complex form like this one, or in complete square. And this one is because of the f naught we have here. So if you look here, you have complex conjugate poles. And if you look here, you have a pole that is s is equal to 0. So this can be written in partial fraction alpha 1 over s plus beta 1 s plus gamma plus over s squared plus 2s. Now, if we multiply alpha 1 by this, and then this term by this, we equate between the left-hand side and right-hand side, we get the following equations. X1 will be this one. This is what we wrote here. Now we equate the numerator f1, f0, sorry, will be equal to alpha 1. This is alpha 1 here. Multiply by this term. This term we found it to be simply This one should be simply s squared plus 2s plus 5. So it is here alpha 1 times s squared plus 2s plus 5 plus, and then beta 1 s times s, beta 1 s times s, which is beta 1 s squared, and then gamma 1 times s, gamma 1 times s. We equate the left-hand side with the right-hand side, and we will say the coefficient of s squared are 0 because I have 0 on the left-hand side. The coefficient of s are 0 because I have 0 on the left-hand side. And 5 alpha 1 will be equal to f naught. And this is it. Coefficient of s to the power 0 will give you f naught is equal to 5 alpha 1, or alpha 1 will be equal to f naught over 5. Similarly, 2 alpha 1 plus gamma 1 is equal to 0. So gamma 1 will be minus 2 alpha 1 over 5. And then we have alpha 1 plus beta 1, which is this one. The coefficient of s squared is equal to 0. So beta 1 will be minus alpha 1, or minus f naught over 5. So we found all the coefficient in terms of alpha 1. So our x1 will be written like this. F naught over s plus 1 square plus 2 square. F naught, we found it to be f naught over 5, which is alpha naught. This is alpha naught, f naught over 5 over s, plus f naught over 5, s plus 2 here, divided by s plus 1 square. And then this is minus here, if you see, this is what we found. And we found gamma 1 minus 2 and beta 1 f naught. So if we take minus common, so this one will be minus 2 f naught over 5 for gamma 1, and beta 1 will be simply minus f naught over 5. So this will stay as it is. And if you take f naught over 5 here, it's the same. I'm just writing this one, Shabab, s plus 2. I'm writing it like this, s plus 1 plus 1 equal s plus 2. And these two, I'm writing just s plus 1 plus 1. Then I have denominator s plus 1. I want to have in the numerator s plus 1. So I have s plus 1 here. And I have the 1 here. The 1 here. I want to bring the, since I have omega is equal to 2, I will multiply by 2 and divide by 2. When I multiply by 2 and divide by 2, so as if I have nothing. So s plus 1 will remain as it is, as if it was s plus 2 in the beginning, the same. So at the end, what we will have the following. We'll have f naught over 5. This is the inverse Laplace transform of f naught over 5 will be simply a step function. This is a step function, f naught over 5 here. And then minus f naught over 5 here, as you can see. This one, s plus 1 over s plus 1, the whole square plus 2 square. It's a cosine term that is shifted with minus 1. That's why I have an exponential minus 2. And omega, the frequency is 2. So exponential minus t cosine 2t. And then plus half, this is half. And this is omega. So this one will be exponential minus omega minus t sine 2t. And this is the solution of x1. F naught over 5. If you take f naught over 5 common, it will be 1 minus exponential minus t cosine 2t plus half sine 2t. This is x1 only. X1 only. We did not find the solution, the total solution. If you remember, we wrote the solution to be like this. X was x1 plus x2. And x2 is related by x1. This is x1 exponential minus t0s. So there is a relationship between x1 and x2. This is it. If we know x1, we will be able to know x2 because they are related by this relation. This property we will be using it like this. So we said x2 will be minus x1 times exponential minus t0s. And then we use a property of Laplace transform for the shifted theorem. This will tell you Laplace transform of ft minus t. Yes, it is initial force, but we did not give the magnitude. It will stay f naught. It will stay f naught. F naught is the magnitude of the impulse, but we did not give it to you. You can give any number at the end. F naught from here to here. F naught. You can give any number. So this will be Fs times exponential minus st0, Laplace transform for it. Or the inverse Laplace transform of this will give you this one. So either this or this. So that's why I'm putting here, it's go back and forth. So x2 will be, in this case, we know x1. Since we know x1, we have x1. x1 is this expression here. x1, we found it. So now if I want x2, I will multiply I will substitute every time by t minus t0. This is the expression of x1. So x2 will be f naught over 5 exponential minus t minus t0 cosine 2 t minus t0 plus half sine t minus t0. Then here, since it is multiplied by this, you have to change every time by t minus t0. And this is what we did. The final solution will be x1 plus x2. x1 plus x2 will give you, this is x1, the blue one, and x2 will be this one, the red one. So this is because x1, and this is because of x2 that is shifted with time at t is equal to t0. I know it's a little bit lengthy, but this is, you should know, at least you should know about it. Another example here, Shabab, which is the same thing as the shifted. We have an initial value problem, y double dash plus y is equal u of t, y0 is equal to 1, y dot 0 is equal to 1, and u of t is given by this signal. This is u of t, or the right-hand side term. What is this, Shabab? If you remember, when you see the arrow like this means it's the impulse, delta. Since there is a time period at the time that is delaying here, so this will be delta t minus 2 pi. Delta t minus 2 pi, and time is delayed by 2 pi. You know the Laplace transform of delta t, the magnitude here is 1. The magnitude is 1, as you can see. So Laplace transform of delta t is simply equal to 1, but Laplace transform of delta t that is shifted by 2 pi will be 1 exponential minus 2 pi s. Minus 2. That's why we are writing exponential minus 2 pi s for Laplace transform of delta t minus 2 pi. This delta t minus 2 pi is an impulse that is starting late after 2 pi. So now if we take Laplace transform of both sides of this equation here, we got this one. We got s square y of s minus s square y of s minus s for this one, and then y of s for this one, and Laplace transform of y of t will be exponential minus 2 pi s. All you have to do now is to solve for y of s. What is y of s? You have y of s common here, you have y of s common here. You solve for y of s, and you will find y of s will be equal to s, this one you take it there, divided by s squared plus 1, plus exponential minus 2 pi s, s squared plus 1. The inverse Laplace transform of s over s squared plus 1 is cosine t. And then the inverse Laplace transform of 1 over s squared plus 1 is sine t, sine. But since it is shifted with 2 pi s, it will be sine t minus 2 pi plus u t minus 2 pi. So this is the solution. You can write it like this. Or since t minus 2 pi هو نفسه sine t, you can write it either like this. Y of t is cosine t from 0 to 2 pi. So from here to here, the solution will be cosine 2 cosine t. Or when t is greater than 2 pi, the solution will be cosine t plus sine t. Cosine t plus sine t. So this will be after the time t is equal to 2 pi. If you look at the response, Shabab, you will see that your the function, how it's behaving is like this. I will reduce the size a little bit. This is how we wrote MATLAB program for writing. Here, we are interested at this point when t is equal to 2 pi. The equation was behaving normal. Then all of a sudden at 2 pi, this is time, t is equal to 2 pi. When t is equal to 2 pi, there was a jump, big jump هنا. شوف الجump هنا. It was, شوف الامplitude, it was 1, شوف الامplitude, now it has increased. And it will stay like this. Because of this, we apply the impulse at this point. So we apply a huge force to your system, and your system is starting behaving like this. This is just the plot for the Laplace transform. How did we plot it? The last point. تفضل.
زاد فضلك بس سؤال بس على البريفيس سلايد.
تفضل.
البريفيس سلايد بس عشان اللي قبله بعد. هنا بس بالبيريد اللي تحت واي اوف تي كوساين اوف تي، وبعد عندنا تحت كوساين اوف تي وساين اوف تي بلس ساين اوف تي. ليش هنا ما في فوق، ما في ساين اوف تي اللي فوق بس كوساين تي؟
If you look this one, this expression sin t minus 2 pi هي نفسها sin t.
حلو.
So this one
حلو.
can be replaced by sin t.
حلو.
So we will have, for when the time is greater than 2 pi, when the time is greater than 2 pi, we have this term plus this term, the two terms. But when the time is just from here to here, this is the solution. Cosine t. When the time is greater than here, we have the both solution, this and this. This plus this. They will be added.
يعني فاهم، بس أنا ليش من 2 باي وأقل ما فيه بلس ساين تي not included.
You know, only this term, it's this one. We have only this term. This term is cosine t. This one will become after. Exponential minus 2 pi s will become after. This exponential minus 2 pi s is here for this term. And this term will be this only. Okay?
Okay.
Any question? تفضل ناصر. طيب شباب now لا it's not true. It's not true. Now شباب, we have a problem, another problem here to be solved. I want you to pay attention. I want you to pay attention. We have a problem that is given by this y double dash plus y is equal to g of t. G of t is this one. G of t is a random, which is r of t if you want. G of t is equal to t. ما عندك مشكلة في هذه. G of t is equal to t. يعني G of s will be simply 1 over s square. 1 over s square. ما عندنا مشكلة. بس هي as if you look here, he's giving you y of pi. He's not giving you y. When we say initial value problem, هنا initial conditions are not at zero. So فيها problem. How to solve this problem? Usually we define Laplace transform. We give you the initial conditions y0 and y dot 0. But here they are not given. y0 and y dot 0 are not given. How to solve this problem, Shabab? Do you have an idea? That's why we are saying Laplace transform of the derivative is to have the initial conditions at time t is equal to 0. Initial conditions at time t is equal to 0 are not given in this problem. Initial conditions are given at time t is equal to pi. Yani conditions, we cannot say initial, but conditions are given at time t is equal to pi. What we do in this case? A problem like this, in this case, we cannot solve it. What we will do? We will do the following. We will assume, Shabab, we will assume that y0 is equal to y0 and y dot 0 is equal to y dot 0. And then we solve problem as if those are given. These are given. And then at the end, we substitute y dot of pi to find what is 0, and we substitute y pi to find y of 0. If you follow me step by step, we will do it this way. So we assume y0 is equal to y0, y dot 0 is equal to that 0, and we take Laplace transform of both sides. We already gave you g of t is equal to t. So s squared y of s minus sy0 minus y dot of 0 plus y of s is equal to 1 over s squared. So we have s squared y of s minus sy0 minus y dot of 0 plus y of s is equal to 1 over s squared. Now we solve for y of s. We find what is y of s. We found y of s to be like this: 1 over s squared plus 1, y0 s over s squared plus 1, y dot 0 times 1 over s squared plus 1. You remember, Shabab, هذا exercise we solved it before. We found that 1 over s squared times s squared plus 1 will be this amount. So I will substitute this by this here, and then I will have y naught y0 times s over s squared plus 1 plus y dot over 1 s squared plus 1. This term, Shabab, هنا, it will turns out to be simply 1 over s squared, and I will take 1 from here. هنا عندي y0 s squared plus 1, وهي عندي 1 over s squared plus 1. I take s squared plus 1 common من هنا وهنا. So I will have 1 over s squared plus y s over s squared plus 1 plus y naught minus 1 over s squared plus 1. So now if I take, Shabab, هنا the inverse Laplace transform of this one will give me t. This one will give me y0 cosine t. And this one will give me y0 minus 1 sine t. Now I take the derivative, y prime. It will be 1 minus y0 sine t plus y dot 0 minus 1 cosine t. Now I have my solution, but I need to find what is y0 and what is y dot 0. If you go back to y pi, y of pi was given to us to be equal to pi. So pi plus y0 minus 1, so y0 will be equal to pi. And y dot pi will be equal 1 minus 0 plus y dot 0 minus 1 multiplied by minus 1 will give you y0 is equal to 2. You substitute y0 and y dot 0, and you will find the solution to be this one: t plus pi cosine t plus sine t. I will stop here. There is another problem to be solved by using Laplace, but we can use it in the lab, inshallah. In the lab, this one, we will be using it in the lab. I will show you the power of MATLAB using MATLAB, the power of MATLAB using MATLAB by solving this differential equation problem. Let me just take the attendance if you give me a chance to take the attendance. The exam, Shabab, as I mentioned, it will be on 23rd of July. I think it's ثلاثاء, from, let's say, 7:30 to 9 or 9:30.
والكويز دكتور متى؟
Everything is in the syllabus. The quiz is this coming Tuesday. ظهرت وما تقراوا الاعلانات. احنا حطينا لكم اعلان خاص بالكويز، بس الظاهر ما تقراوا.
هذا دكتور تبع اللاب ولا الليكتشر؟ الاعلان
الاعلان خاص بالليكتشر يا ابني. في الكويز ما عندنا كويز في اللاب، ما عندنا كويز في اللاب، عندنا كويز في الليكتشر. العلوة موجود. الدغالبي موجود شباب؟
يس دكتور موجود.
اهلا وسهلا. المسعودي موجود؟
يس دكتور موجود.
مسعودي كيف حالك يا ولد؟
الحمد لله.
ملا ماجد ملا اهلا. الصوت شباب يا ريت لو تنقصوا الصوت. حسين حسين القحطاني.
يس دكتور يس.
كيف حالك؟
نحمد الله. كيف حالك دكتور؟
الله يبارك فيك. المحمدي. محمدي كيفك يا أخي؟
بخير الحمد لله. اخبارك؟
يحيى عباس. يحيى عباس. شباب بليز تراي تو ريد ذا نوتس تاع توداي، لانه بكره راح يكون عندنا لاب، او في بعضكم يبدا اللاب اليوم. it will be very helpful to solve the lab for Laplace transform. اليحيى عباس. عباس قحطاني. عبد الكريم قحطاني.
حاضر.
اهلا. شهري علي. علي كيفك يا علي؟ رميح هاني. القرني علي. علي كيفك يا علي؟ زهراني فارس الزهراني.
موجود فارس الزهراني.
الحمدان سلم لي عليه فارس الزهراني اذا شفته يا فارس.
طيب.
الحمدان عبد العزيز حمدان. الحمدان عبد العزيز. شريدة موجود.
شريدة محمد صح؟
ايوه
اي موجود.
العجمي مبارك العجمي. موجود. مبارك العجمي موجود. طيب الطليحي يوسف.
موجود يا دكتور موجود.
اهلا وسهلا. الزاير سلمان كيفك يا سلمان؟ الجهني نادر. اهلا وسهلا. العقيل رائد.
يا هلا والله.
مشرفتنا يا رائد اليوم ما شاء الله عليك.
الشرف
حاضر.
مبسوطين انه سمعنا صوتك اليوم درويش.
الله يسلمك دكتور.
حسين كيفك يا حسين؟